Okay, so oxidation of sputters of Ti6Al4V right, during photometric fusion laser beam. Here are the contents, a bit of background, why we are studying sputters, experimental methodology, results, and conclusion. Okay, let's go with background. Yeah. So to increase the robustness and sustainability of laser photometric fusion process, we need to increase the reusability. And why we need that? To reduce the cost and improve the quality and reproducibility. But there are challenges like powder degradation, which usually happens with powder oxidation, although it is not that common in case of laser photometric fusion because we are mostly working at room temperature or close to room temperature. But in case of electron beam, it could be a big issue. And second is sputter formation, which is very common in laser. And it is the main kind of, you can say, criminal in powder degradation when it comes to photometric fusion laser beam process. And why I'm saying that? Well, it is proved in our study on aluminum, silicon, and magnesium, where we reuse or saw this powder after 5,000 machine hours. And what we saw after like aluminum 30 represent 30 months, we saw that there are some sputters, these bright particles appeared after reuse, and the amount of these or the numbers reached around 3% after 5,000 machine hours. And when we looked at the surface of these sputters, they are covered with oxide, very thick oxide with 75 to 125 nanometer the oxide layer thickness. And then we looked, okay, this is oxidizing aluminum is kind of oxidizing this way. Does all the alloys oxidize in similar fashion? We did this alloy sum 1.8 and checked the sputters. Well, it is quite different. In alloy sum 1.8, we saw some particulate formation and some patches, oxide patches formation. So that is where our curiosity began to look into Ti6Al4V, which has titanium and aluminum, both are very oxidation friendly, I can say. And well, that's why we thought of looking into that. And another thing, gases can affect, as we saw in Sophie's presentation yesterday, on the generation or amount of sputters. So we kind of combined that study with this one to see oxidation and also the effect of gases. So we used 3 different gases, argon, helium, and a mixture of argon and helium. And sputters got generated. We collected sputters from gas outlet, gas inlet, and tried to evaluate those sputters. And compare the effect of 3 different gases on it. We did SEM analysis, then bulk oxygen, nitrogen, hydrogen analysis. Then we did a very comprehensive XPS, AES, and nanosims, TEM analysis to analyze the thickness and nature of oxide layer. So the people who don't know about XPS, well, XPS is a very surface sensitive technique where we can measure the chemistry and also the chemical state in the range of 1 nanometer to 10 nanometer. And with ion etching, we can do also chemical profiling with the depth. And it is good for quantitative and statistical analysis. But there are some cons, like we cannot see the particle itself, so we cannot do a very localized analysis. And also, when a complex alloy comes in play, differentiating between different mixed nature of oxide gets complicated at times. To resolve the problem of localized analysis, we had the opportunity to do AES in our campus. So we did AES. AES is also a very surface sensitive technique where you can measure 1 to 5 nanometer. And as you know that it is using electrons, so we have SEM detector and you can see the particle, you can locate the position where you want to do the analysis. And so that is a major benefit of AES over XPS, but it is a very qualitative analysis rather than quantitative, which we have in XPS. And also issue we have with XPS, that mixed nature can be difficult to differentiate. For that, nanosims can be used, where you can use, like you bombard ions, and those ions generate secondary ions, and you can detect those ions and kind of try to navigate, okay, what type of mixed nature of oxides are there. Okay, so let's move on to results. Okay, this is what we saw, and also yesterday Sophie showed that, okay, the amount of sputters, she showed it through OT, that the amount of sputters are decreasing with use of or introduction of helium. And there was a question that, are they only cold sputters, or they are or hot sputters, because helium has very good heat conductivity, so they are cooling very fast. Here we found that the total amount of sputters decreased. It is both cold and hot. So with the introduction of helium, the amount of sputters can be decreased significantly if you compare both values. And if we compare the chemical analysis with virgin, argon, and mixture and helium, the oxygen pickup in all three gases, you can see argon has the highest oxygen pickup, followed by both mixture and helium. And if you see the nitrogen pickup, that is kind of more significant here in case of argon, like 3 times, and it is not that prominent in case of helium and mixture. And if we compare the morphology, then I focused on the oxidation of sputters, and I more focused on the sputters we obtained from argon environment. And if we compare the morphology, on the low magnification, particles look same, very fine sphericity. But if we go to high magnification, we see some particulate formation on top of it, on the particles. And if we come back to Ti6Al4, we know we have very stable oxide layer on the surface of Ti6Al4. So how these particulates are forming? So that question came to our mind too. So there were 2 options there, condensation or diffusion. Like condensation is happening from the melt pool, vapors are going and depositing on the sputter surface, which have gathered in the gas outlet. And second option was the diffusion, like atoms are going through this stable oxide layer. And to check that or to confirm that, we did this experiment where we placed the copper plates in gas outlet and try to capture that condensation and try to analyze and compare with the sputters if it is the same or is it different. And what we found on that copper plate, okay, you get a very fibrous condensate deposited on the surface. But if we compare it with the sputter, it is quite different. It is not the same. And also, if you go back to the gas outlet and try to imagine if sputter lens of sputter coming later on will kind of deposit on top of it, and it will not have enough chance to get too much sputter. So there might be, too much condensate. So there might be a little bit condensate in during that process, but it is not as much. Okay. And then we did some AES analysis and tried to compare virgin and the sputter's surface. And in virgin, you can see titanium here and oxygen, and aluminum is a bit lower. What is the difference in case of sputter? It is very much enriched with aluminum along with titanium. So that sputter and solidification or cooling process is giving aluminum a chance to go to the surface and oxidize. Then we further looked into the, it is not moving.
Please try again.
Okay, thank you. So we try to detect or identify the sputter types. There are 3 different types of sputters. One sputter, like virgin-like, not changed much. Second type is extremely oxidized, very granular structure on top of it. And third one is kind of recrystallized, where you see a metastatic structure on top of it. So not all the spotters are same, depending on the origin of spotters or the temperature they are ejected, they can vary extremely. And we did AES again on top of it and saw, okay, what is the difference and what is the chemistry and the extent of oxidation, virgin-like, very sharp decrease in oxygen and very sharp pickup in oxygen or titanium. So it means that oxide layer thickness is quite low. While in case of recrystallized, there is a plateau forming here. So it means that there is a little bit more oxidation in case of this recrystallized as compared to the virgin one. So they have some kind of interaction with the oxygen present in the chamber. And in oxidized one, we see a very thick oxide layer, probably have like it is around 75 nanometer on the calibration scale of tantalum oxide. So different type of spotters oxidizing differently. Then we did some XPS analysis. I'm omitting XPS detail analysis, which will be in the paper, but here I have put just the measurement we did for oxide layer thickness and comparison. In case of virgin, it was around 10-12 nanometer. So just to clarify, it is on tantalum oxide scale, so it might be not that precise if we compare it with the TEM analysis, the oxide layer thickness. So we had to do some readjustment in the end to precisely measure it on tantalum oxide scale because I'm comparing it, so that's why I put it like this. There's a big pickup or increase in oxide layer thickness from virgin to argon. And in helium and mixture, there is also an increase, but increase is a bit lesser than argon environment. To precisely measure the oxide layer thickness, we then did some TEM analysis. And in TEM analysis, we can see that it is around 12 nanometer. And if we redo the adjustment of tantalum oxide with the etching rate of aluminum oxide and titanium oxide, we will reach about the similar value. Now the only question remained, okay, if oxide is forming, is it mixed oxide, spinel type oxide? What is the nature of oxide? For that, it was kind of very complicated to analyze through XPS analysis. So we did some nanosims analysis where we can see the different like aluminum oxide, titanium oxide, and the location on the particle. And from the location, we can see that aluminum and titanium does not have a very similar location, and also aluminum is much lower in case of as compared to titanium in case of fresh powder. There are some points where you can see mixed aluminum and titanium oxide formation, but in case of spotters, it is complete overlap. You can observe here. Which means that in case of spotters, we see a much more mixed type of oxide as compared to the individual oxide, which is the case for fresh powder. Okay, so that was all. I will conclude my presentation of spotters. Spotters from different alloys oxidize differently, and element susceptible to oxidation has the priority when it comes to oxidation. Choice of gas affects the oxygen, nitrogen, and hydrogen pickup. Spotter particles show the formation of aluminum-rich particulate formation on the spotter surface. And oxide particulate formation is driven by diffusion and not much by the condensation. And spotter of Ti6Al4V can be divided into three different, or the categories we identified in three different categories: virgin-like, which are not much affected, recrystallized, and oxidized. And AES analysis show the extent of spotter oxidation relies upon that type which we identified. And argon environment showed the highest increase in oxide layer thickness as compared to helium or mixture. And the nature of oxide on spotter was mixed, mostly mixed in case of spotters as compared to the virgin particles. Yes. Question.